So in this video, we are going to learn to use 3D CAD geometry and solid elements to work an example that we've done previously using one-dimensional beam elements. So we are looking at these two rods, AB and BC, connected together and loaded with a 10 kip at B. The wall is fixed at A, and the wall at C has a clearance of 0.002 inches. So in order to use solid elements, we are going to need to create a 3D geometry, and we're going to do that in Design Modeler as well. Everything we have done to use beam elements was basically using the modeling feature. Today, we're going to be using Sketcher to create a sketch, and then we're going to either extrude or revolve to create our bodies to make our parts. So that's the problem we want to solve. We're going to continue to use the radius for AB and radius for BC. So I'm going to open a new Workbench project. So this is still unsaved. First thing I want to check are my units. I want to make sure I am using US customary to use inch and pound. So I'm going to be using US engineering units. I want to make sure that I am displaying the values in project units. I am going to save my project. So I'm going to save as. I'm going to choose my folder, and I'm going to create a file. I'm just going to call it first solid elements example. Okay, so we saved our project. And next, I'm going to create an analysis system. And again, we're doing a static structure system. I'm going to go to my second step, which is engineering data. I double click on engineering data, and I need to create a material that has a modulus of elasticity of 10 million psi. So I'm going to click here to add new material. I'm going to call my material again class example. And this material has a linear elastic behavior. So from toolbox, I'm going to click linear elastic, and I'm going to double click isotropic elasticity. For Young's modulus, I'm going to put 1 e to the 7 for 10 million psi. For Poisson's ratio, I'm going to go with a 0.3 like most metals. So my material is defined. I'm going to toggle back to project. And next, I'm going to right click on geometry and choose new design modeler geometry. So this launched design modeler. I'm going to turn on my default planes, X, Y, Z, X, and Y, Z. And I still want my part to have the axis of the part oriented along the X axis. So in order to do that, I'm going to sketch a section. If I'm going to be using extrude, I'm going to sketch my section on the YZ plane. So in order to create a sketch, I can use from the toolbar menu this sketch, new sketch. But before I do that, I want to make sure to select the proper plane. So if I want to sketch on the YZ, I'm going to come here and check the YZ plane. And I'm going to say a new sketch. So sketch 1 is created as a child of the YZ plane. To see it more clearly, I'm going to select my x-axis. So now I'm looking at the y-z plane. And I want to start with the section or the sketch for AB that has a radius of 0.56419 of an inch. So now all what I have to do is to create a circle, and now we're going to be using the sketching tool in Design Modeler. So I'm going to toggle here to sketching, and under the sketching, I have the sketching toolboxes. I can draw a line, or in this case, I need to pick a circle. So I pick a circle, and we want to be careful here with our automatic constraints. By default, these should be turned on. If they're not turned on, you're going to go to constraints, and you want to go all the way down to make sure that auto constraints is turned on. So I have my auto constraints turned on, and again, that should be the default. Now I'm going to go back to draw, and I'm going to select a circle, and I want the center of the circle to be constrained to the origin. So as I move around, you see when I get close to the axis, I see the letter C. I really want to see the letter P to mean that it's constrained to a point. And once I see that, I'm going to do a click, and now I can draw my circle. You want to be careful here. If I look at my ruler, my units are still showing in meters. I need to change that to inches, and it's really going to be a very small circle based on that scale. So I'm going to start with something very small. I'm going to go to my units, and I'm going to change that to inches. And now I'm going to go to dimensions, and I'm going to pick a radius. I'm going to select my circle, and now I have a radius R1. As you can see here, if I look in the detail view, R1 is like 37 inches. Mine is definitely much smaller, so I'm going to zoom in and come here in the detail and change the dimension to put my 0.56419. And I click enter. So now you see the ruler, and we see the scale, and we have the sketch that we need to extrude to create the part A, B. The sketcher is shown here in light blue. If I toggle back to modeling, it's showing in yellow. If I click generate, the color changed to dark blue. Now I can use my sketch to extrude and create the part AB. So I'm going to go to, from the toolbar menu, I have the extrude option. So I'm going to select extrude. And now it is asking me to select a geometry. So the first step, I'm going to select my sketch and go apply. So sketch 1 is selected. And it is showing the direction in which the extrude is going to happen. And the direction here is normal. And the extent is fixed. And now I need to specify the depth. So AB was 10 inches long. So I'm going to change that 12 to 10 inches. And I'm going to say enter. And we can look here at what our part, or how our part is going to be extruded. If I like what I see, I'm going to select generate. Before I select generate, I want you to pay attention that as of now, I have 0 parts, 0 bodies. When I'm extruding, the operation I'm doing here is I'm adding material. So I'm going to select generate, and here comes our first body, which is a solid body. So this is a true solid geometry. Next, I want to create BC. And BC has a slightly larger diameter. So the diameter of C is 0.690988. So now I really need to create a new sketch, and I'm gonna create that sketch on a new plane that I'm gonna create at the end of the face here. So I want to create a new plane. So I can come here and choose to create a new plane. I can go create and choose new plane. And now it's calling it plane 4. And the type, I'm going to choose rather than from plane, from face. And it's asking me to select a base face. So I'm going to come here and select for the geometry. I want to select the front face of AB at point B. And I'm going to say apply. And I'm going to click generate. And now I have a new plane parallel to YZ. I'm going to select plane 4. So plane 4 is selected, and I can see it here in the toolbar menu. And I want to create a new sketch that is a child of plane 4, or rather on plane 4. So I'm going to select a new sketch. So you see sketch 2 is going under plane 4. To look at it, again, I'm going to select the x-axis, and then we are working on plane 4. And I'm going to again toggle to sketching. I'm going to draw another circle. I want to see the letter P, and this is going to be slightly smaller than the original, the first circle. So here is my circle. I'm going to go to dimensions. I'm going to put a dimension to the new circle. And I want to be careful because I accidentally here selected the circle, and I'm creating, I'm defining a diameter, not the radius. So I'm going to cancel that, and I'm go specifically select the radius. And now I'm going to go to the circle, and here is the circle, the radius R2. I'm going to go to the detail view and make sure to specify the correct dimension. So I put here the 0.690988, and I'm going to click generate. If I toggle to modeling, under plane 4, we can now see sketch 2. That's the one we want to do another extrude, and we're going to use sketch 2. So I'm going to show again my 3D view, the isometric. I'm looking at it here. And I'm going to do another extrude. And I'm going to select my sketch 2. Apply. So sketch 2 has been selected. And I'm adding material because I want to have one part. And I'm going to extrude. This time it is 12 inches. And I'm going to click generate. Because I used add material, we just added to the existing body. So I ended up with one part, one body. I do not need to form a new part like we did when we use beam elements. My geometry is done. And if I'm happy with it, I can save my project. So I can click save here. That will update my project. I'm going to go back to Workbench. So I have a green check mark next to the geometry. So next, I'm going to go to step 4. I'm going to double click model. And this was starting ANSYS mechanical. So here is the ANSYS mechanical. If I select on geometry, we see that we inherited the geometry from that we created using design modeler. First thing, I want to fix my units. So I'm going to go to home, tools, units, and I want to make sure I'm using US customary using inches and pound forces. So I pick that one, and you see the ruler here was changed to inches. Next, I want to assign the material to the geometry. So if you look here, when I'm selecting the geometry, if I expand, I have that solid. And you see the material assigned to my geometry is the default structural steel. So I'm gonna want to go to the assignment of the material, click the arrow to the right, and now I have a list of the material, and I can see the class example material. So I'm gonna select class example. Now class example material is assigned to my solid part. Next, we want to create our mesh. So I can go to mesh, and I can right click, and I can choose to generate a mesh. And we can see the elements here, and I want you to pay attention to how the elements were placed within the geometry. And if you inspect that, you see that we have surfaces that are not cylindrical. I can see the flat edges of the elements. So I'm not really closely mapping my geometry. So we have a room to refine that to better capture the geometry. Can I still run it like this? Yes, but this is a coarse mesh, and the part is going to get distorted, is not going to behave as we expect. And this is something you can play with. But I'm going to show you here how to refine the mesh. So I'm going to go to mesh, and I want to make sure my context, a mesh, is selected. And I'm going to go to sizing. And when we look here in the details of sizing, the default element size is 1 inch. And this is a large element to fit within that small geometry. So within the geometry, there is no geometry yet selected. So I'm going to come here, and I want to select my solid. So I want to go to my sizing again. And for the geometry, I want to select the 2 pieces. And I want to make sure I'm not selecting the surfaces, but rather the solid. So I'm going to come here and choose a body. And I'm going to come now and can do 1 click. And this makes sure I'm selecting the entire body. So again, I changed from the smart select to the body select to allow me to select the body. So I'm going to apply that. And I'm going to go to the element size. And I think to capture the surface and keep it cylinder, I'm going to try using a 0.2 inch for the size. So I'm going to put a 0.2 inch. And now I'm going to click generate again. And let's look at the mesh that we're getting. So we're using much smaller element, and I have a much more uniform mesh. So this is a much nicer mesh than what we originally had. So now we're done with the geometry, with the material, and with the mesh. We have 2 more steps remaining in the pre-process, which is to define the constraints, the supports, and to apply the loads. So I'm going to go to static structure, and under context, I have environment. And if we look at the supports, I want to point out that if I click supports, I no longer have simply supported because I am not using any beam element. So that support is grayed out. We are dealing with different types of elements, and we have to be conscious about our constraints. When I'm working on 3D, each point has only 3 degrees of freedom. Translation in X, translation in Y, and translation in Z. So there is nothing such, when I say like a fixed support, it does not fix rotational degrees of freedom, but it fixes the 3 translational degrees of freedom. And we're going to talk more about that when we start modeling beams using 3D geometry and solid elements. So if I look at my problem, my A point or the face at A is completely fixed, is attached to a wall. So for that, I can come here and use a fixed support, and I want to apply it to the face at A. So I select the face at A for a fixed support and say apply. And now the face at A is being fully constrained, meaning all the face, 3 translational degrees of freedom are restrained. Next, at point B or face at B, my part is going to displace along the X direction a 0.002 inch. So I'm going to use the displacement constraint like we did when we use beam elements. And I'm going to select, see, I have here a displacement support or constraint. First, I need to select my geometry. So I'm going to select the face at C, and I'm going to go apply. And I'm for the X component, I'm going to put a 0.002 inches. And in the Y direction is really going nowhere, so I'm going to put a 0. And for the Z direction, I'm going to put a 0. So now I have my 2 constraints at A and at C, but I do not have the force applied yet. Now, in real life, when you have a problem like this, you need to have a flange or a surface to load your part. So in this case here, I'm going to use that face that I'm highlighting in green to apply my 10 kip load, 10,000 pounds. Now, because this is all symmetric, it's like I have a circular section here. The resultant is going to be going through the axis. So it is not applied on the axis, it's applied to that outer surface, but the resultant is going to be going to the axis. So again, we're going to use a force, and I'm looking here at the tail of a force. So I need to select a face. A face is selected. I'm going to say apply. So that's red face where the force is going to be applied. I'm going to define my force using components. So I'm going to go define by and change that vector to components. And my force is applied in the X direction. And I have 10,000 or 1e to the 4. So that's a 10,000 pound force. Let's look at this and revise everything that we've done. We have our 2 supports and our 10,000 pound force applied at B. So this, I'm able to capture my original problem. We included everything that is given in the statement. It is now time to run the engine, to put together the matrices and solve the equations to find some answers. So if I click solve, I'm going to look at this flash icon, the yellow. If I have a good model, it should turn to a green check mark. So clicking solve, work in progress, building the mathematical model, solving, writing results, and I do have a green check mark, meaning we can start looking at a solution. So the next step, I'm going to go to solution, and we want to look for the wall reactions. I still want to look at the displacement at B, displacement of point B, and we want to look at the stresses. Now, I'm no longer dealing with a 2-force member, but rather with a solid part. So I really cannot find the axial force, but I can find the axial stress. Okay. So we're going to be looking for these three things. So I'm going to start with reactions and displacement. But before I do that, I always like to do like a check and look at the behavior of the part to make sure my part is behaving as I expect. So I'm going to go to the results and I'm going to check deformation and I'm going to do total deformation, right? Another one that I can do is I can go results, deformation, and I do directional and choose the x-axis. I can come here and click the directional deformation and choose to rename it based on definition. So that is going to change the name. It's just going to call it x-axis directional deformation. I'm going to click solve and look at this. Everything is positive for the directional, meaning everything is heading in the positive x direction, which is what we expect. Our part is fixed to the left and the force is applied to the right. AB is pulled and is in tension, and BC is getting compressed, but it's still moving to the right. And if we look at the animation, we can see that type of behavior. I see that AB is being stretched and BC is being compressed. So we like the behavior, it's behaving as expected. So the next step here is to start looking at the specific results that we are interested in. So I'm going to go to solution and I'm going to go to probe and I'm going to select a force reaction. And here I have the details of a force reaction. I'm going to continue to use for the location method. I don't want to change the default boundary condition. So I'm going to first choose fixed support for the reaction at A. Next, I'm going to do another probe and pick a force reaction. And now I'm going to pick displacement for the reaction at C. So I can come here and change the name of that, rename it, call this the reaction at C. And the first one, I'm going to rename it and call it the reaction at A, force reaction at A. Let's solve for these and check if we get something similar to what we got earlier. So looking at the total, I'm getting 5,490. When we work this problem by hand and using the beam method, we got 5,555. So you see there is a very small percent error, but the answer is within acceptable range. Let's look at the force reaction at C. And I'm getting 4,509. When we did it by hand, we got 4,444. So again, there is an error of about like less than 1%. So this is a very acceptable answer that we're getting here using this mesh. Next, I'm gonna create a probe to find the deformation at point B. So in order to do that, I wanna make sure I'm not picking an edge, but rather selecting a face. So right here, I'm selecting the face where I applied the force. I'm gonna say apply. And I'm gonna specifically look at the displacement in the X direction. So I pick the X axis. I'm gonna solve. And I'm getting here the maximum deformation that we have seen of a 0.006 inches. And when I did this by hand, I got a 0.00555 inches. So there is a slight error, which is expected in a numerical method, especially with all these elements that were fitting within the geometry. Next, I'm going to show you how to find the stresses within the part. So we're looking here at two pieces and we expect, or two rods, AB and BC. We expect AB to be in compression, or we know AB is in compression and BC is in tension. So I'm going to go to solution and I'm gonna go to results, and I'm gonna select the stress, and we have all the different types of stresses we can look at. If I want to look at the axial stresses, it is a normal stress, and more specifically, a normal stress in the x direction along the axis of the part. So I'm going to select normal, and I want to come here and make sure that the orientation is selected along the x-axis. So I'm going to continue to use the x-axis. This is important because if you have an axially loaded part that is oriented along the y-axis, you're going to need to change that and make it the y-axis. So I'm selecting here the axis of my part. Now, if I click Solve, we're going to see the stress distribution within our two parts. And I want to show you here that if I select a probe and go anywhere within the part, I'm seeing the stress of 5,490 psi, which is really the force divided by the area, and the area is 1 square inch. So that tells us that the axial force is 5,490 pounds. So I cannot specifically ask ANSYS to give me the axial force, but if I know the axial stress within the part and multiply it by the area, you can find the axial force within the part. Likewise, I should expect to see compression here. And yes, within the part, I am seeing a negative 3,006 psi. Again, if you want to find the internal force, you multiply by 1.25 square inches, and you get the axial force, and it is in compression. There is a negative sign. Now, you may be looking at the fringe plot here and looking at the scale, and you may be wondering, how about this 9,165? That seems odd. And indeed it is. This is known as a singularity error that I may get with my model. And if you want to see where is that located, I can come here and select maximum. And it is pointing at a point that has a very high stress. And you will see this is close to the discontinuity. So that very elevated stress is somewhere where there is a change in the diameter. And indeed, the stress varies within the elements here, and this is not what I really expect to see. So that's why when I'm using my probe to find the stress in the part, I was not going close to this part where there is the intersection of the pieces, but rather if you pick any point close to midpoint or away from any discontinuities, you should get the right answer. Likewise, if I come here, I'm getting like negative 14,000. Again, this is an error, and I can enhance the performance if I continue to use a finer mesh. But this is the nature of the numerical solution and using the finite element method. So please be careful when reporting the axial stress in these pieces or these rods. You want to make sure if I'm using the probe method, I am going away from any discontinuity or away from the supports. And you see within the part, the stress is pretty uniform as we expect. Okay. So in this example here, we were able to analyze a part that is axially loaded using its 3D CAD model and using solid elements.